Hello and welcome to Corollary 3.26. Let's jump right in. So if we have a set E sub alpha with alpha in A be an orthonormal subset of a Hilbert space H, and M is the smallest closed subspace of H containing E sub alpha, then M is of this form here. Now you'll note here I leave off the subscript, alpha is in A. For the remainder of the video we're going to be leaving off that subscript where confusion doesn't arise, just for simplicity of notation. Alright, so if you'll remember back to theorem 3.25 on the previous page, we have that if I have an orthogonal subset of a Hilbert space, and I take the sum of the squares of its norms and find that it is finite, this is sufficient to show that the sum across that orthogonal set converges. So, this alludes to what we see right here in the definition of our set. So, first we need to show that this set is in fact well defined in the context of our Hilbert space. So let's refer to this set from here on out. Is n what we're trying to show ultimately is that m is equal to n? So, or n is first well defined and then that n is equal to m. But first we'll work on the fact that it's well defined. So you'll see here that in theorem 3.25 the requirement was that we were dealing with the norms of the vectors in our orthogonal subset. Whereas here, I don't have them. I have the coefficients on our orthonormal subset. But because this is an orthonormal subset, all of the norms of E sub alpha are going to be 1, which gives us that these in fact are the norms of our vectors in the sum, or elements of the Hilbert space, that are the lambda alpha times E sub alpha. This is in fact just the norm of those vectors. So that does meet our requirement needed to use theorem 3.25. The only other thing that we need is that this new set, lambda alpha, E alpha, is in fact an orthogonal set. Obviously it is no longer orthonormal because we've changed the all of them. Well, possibly, we've changed some of them, possibly. There's nothing against all of the lambdas being on the unit circle, but they definitely don't need to be. But this new set we claim is in fact also orthogonal. And the reason for this is, if I have two elements, x and y, that are orthogonal, then their inner product is 0. Now, from our basic definitions of a inner product, we have that if I have a coefficient on the first one, this is the same. I'm able to pull it outside of our inner product, and hence we'll still get 0 for the inner product. So putting a scalar on the first element in a inner product does not change the orthogonality or the orthogonality of the vectors. And as well, if I put the coefficient on the second term, we can pull out its complex conjugate. But again, x and y, the inner product of x and y is 0, so this is still 0. So the fact that I've added a coefficient to all of my vectors in an orthonormal subset, or an orthogonal subset in the more general case, does not affect the orthogonality of the subset, though it does affect the orthonormality, but that's not relevant here.